Dear students, let us start the new chapter Electric Potential. This is the second chapter you want to study in your 12th standard syllabus. Electric potential is a scalar quantity that describes the electrostatic nature of around a charge or a charge distribution. We studied electric field in the previous chapter. Electric field is a vector quantity that also describes electrostatic nature around a charge or a charge distribution. Since it is vector quantity, the electric field, higher order calculations become tedious because directional problems comes into play. Since potential is a scalar quantity, no need of specifying the direction. Therefore, the representation of the space around a charge or a charge distribution become little bit easier. We studied the definition of electric potential and all in 10th standard. So this is the charge, source charge. Let us take a positive source charge that creates an electric field around it. Since it is a positive source charge, the electric field is radially outwards as shown in the figure. Now, if I am placing a charge, test charge, positive test charge, there will be repulsion. If this test charge is movable, what happens is this will move away in the direction of electric field till it reaches infinity. Infinity is the point where there is no interaction of this source charge. This is similar to the masses moving under gravity. The stone kept at the top of the mountain will always comes down, that is a spontaneous process or natural process. Similarly, under this electric field, a positive charge will always move to the infinity. And if I want to take a positive charge from infinity to this point, that will not happen automatically. External work needed for that. This is similar to the masses will never go up against the gravity. External work needed in order to move a mass from the bottom of the mountain to the top of the mountain. External work needed. Similarly, in order to move this positive charge against electrostatic field, external work needed. So I am taking a charge q from infinity where there is no interaction to this point. W amount of work is done. Then the potential at this point is defined as amount of work done per unit charge. Potential is equal to amount of work done to move a unit charge from infinity to that point. So potential at A is nothing but total amount of work done divided by total charge which I brought from infinity to this point. So mathematically it can be written as V is equal to W infinity to A divided by Q. Now there exists a potential difference between any 2 points in an electric field. So again I am taking the source charge like this. This is the electric field and I am taking 2 points A and B. VA is the potential at A and VB is the potential at B. Potential at A and potential at B are not equal. If I am considering Q amount of charge at infinity and I am bringing that Q amount of charge to B as well as I am bringing Q amount of charge to A. Since A is closer to the source charge, I want to overcome more force in order to bring charge Q to this point A. So that means more work needed in order to take the charge from infinity to A. So that means more work needed, that means potential of A is more. And B is away from the source charge. Less work only needed to take this charge from infinity to B. Therefore potential of B is less. So potential of A can be written as W infinity to A divided by Q. Potential of B can be written as W infinity to B divided by Q. It is very obvious that the potential of A greater than potential of B, there exists a potential difference between A and B. The potential difference between A and B can be written as delta V is equal to potential of A minus potential of B. Potential of A we already written W infinity to A divided by Q minus W infinity to B divided by Q. So 1 by Q can be taken out. W infinity to A minus W infinity to B, that is nothing but the work needed to take the charge from B to A. So it will be delta V is equal to VA minus VB is equal to WB to A divided by Q. So this is the equation for potential difference. There exists a potential difference between any 2 points in an electric field. Now, what is the unit of potential or potential difference? The unit of potential or potential difference is nothing but unit of work and divided by unit of charge. Unit of work is joule divided by unit of charge is coulomb. Joule per coulomb is also known as volt. Now the next question arises, define 1 volt. What is 1 volt potential or what is 1 volt potential difference? Answer is 1 volt is equal to 1 joule divided by 1 coulomb, means if 1 joule work is needed to take a charge from infinity to a particular point, once again if 1 joule work is needed to take a unit charge from infinity to a particular point, potential of that point is 1 volt. Or how can we define potential difference 1 volt? If 1 joule work is needed to take a unit charge from one point to another in an electric field, the potential difference between those 2 points is 1 volt. Once again, 1 volt potential difference can be defined like this. Imagine if 1 joule work is needed to move a unit charge from one point to another, then the potential difference between these 2 points is said to be 1 volt. Now, we already said the potential describes the same electrostatic field, same electrostatic region around a charge or a charge distribution. Their electric field is also existing. So that means electric field and potential are very much related. Then what is the relation between electric field and potential? That is the next question. So again we are going to take a source charge. This is the source charge that create an electric field, and electric field direction is radially outwards as shown in the figure. Now I am taking 2 points A and B. Potential of A is VA that we already defined. Potential of B is VB that we already defined. There exists a potential difference between A and B that also we already defined. Now let us consider a test charge. A positive charge Q is placed here at B. It experiences a force. And what is a force experienced by the charge Q? F is equal to QE is the force experienced, and the direction of that force will be like this. I'm not writing the vector nature and all. So the direction of the force is like this, in the direction of electric field, since it is positive charge. If this charge was negative, the direction of force would have like this. Now I want to take this charge from B to A. So at least equal and opposite force should be given against this force. Then only I can move the charge against the electric field. So at least equal and opposite force F is equal to minus QE should be given in order to move the charge from B to A externally. Now put as equation number 1. By applying equal and opposite force F is equal to minus QE, I am able to move the charge through a distance dl. Then small amount of work done can be written as dW is equal to F dot dl. Now look at what is the direction of force. This is the direction of force applied, and what is the displacement? This itself is the displacement direction. Theta is equal to 0. Therefore F dot dl can be written as F dl, because cos of 0 is equal to 1. So this is the small amount of work done, and here F can be substituted minus QE. So dW is equal to minus QE dot dl, not dot, into dl. Put as equation number 2. What is this dW? dW is the small amount of work done in order to move the charge Q against the electric field through a small distance dl. My aim is to find total work done in order to move the charge Q from B to A. How can I find out the total work done WB to A? The total work done can be obtained using the method of integration. So using the method of integration, total work done WBA can be written as integral of B to A dW. dW is the small amount of work done we already obtained. Now substituting dW, integral of B to A minus QE dl, where dW is equal to minus QE dl that we already obtained. Now Q is a constant term, can be taken out. WBA is equal to minus Q times integral B to A E dot dl. Now Q can be taken to the left. Then I'll be getting WBA by Q is equal to minus integral B to A E dot E dl, not E dot dl because theta is equal to 0 over there, E into dl. Put as equation number 3. We already studied this particular thing, WBA by Q, in the previous section. We studied that this is nothing but the work done to take a unit charge from B to A. That means it is the potential difference between A and B. So WBA by Q is equal to VA minus VB. This we already studied in the previous section. Put as equation number 4. Look at the left hand side. Look at the left hand side. Left hand side remains same. Therefore right hand side we can equate. When we equate the right hand side, VA minus VB is equal to negative of integral of B to A E dot E into dl. Even if I am saying E dot dl, it is correct only because theta is equal to, even if I am writing E dot dl, it is correct only because theta is equal to 0. If I am not considering theta is equal to 0 here, I can write it is minus integral B to A E dot dl. It's obvious that theta is equal to 0, therefore E dot dl is equal to E dl, that we can do here in this step even. Otherwise you can do that here in this step in the beginning itself. No matter what is the potential difference between 2 points, potential difference between 2 points is a negative line integral of electric field between these 2 points. Integral of E dot dl is the line integral of electric field. When I take line integral of electric field between 2 points and a negative line integral of electric field between 2 points, that comes out to be work done per unit charge. And work done per unit charge is the potential difference. So negative line integral of electric field is nothing but potential difference between 2 points. So this is the equation we have to derive. So VA minus VB is equal to minus of integral B to A E dot dl means negative line integral of electric field between 2 points is nothing but a potential difference between these 2 points. Now I am assuming my point B is at infinity. What is the potential at infinity? Potential at infinity is equal to 0. Since potential at infinity is equal to 0, if I am considering this, now I will be getting potential of any point VA is equal to minus of integral of B is at infinity, infinity to A E dl or E dot dl. So this is the value of potential at a point. This is nothing but the total work done. When I calculate this, we already proved that negative line integral of electric field over any length is the total work done to take a unit charge from a particular point to another point. Here it is the total work done to take a unit charge from infinity to A. The total work done to take a unit charge from infinity to A is nothing but potential of that point. Therefore VA is equal to negative line integral of electric field over a distance infinity to A. So this you have to study as the another equation for potential, or these two equations gives the relation between potential difference and electric field. Now let us consider these 2 points are very close. A and B are very close and there exists a potential difference dV. Since potential difference between A and B is very small, I can write it is as fractional change dV, and the distance between A and B is dx. Why the fractional change is taken? Because I am assuming that A and B is very close. When A and B is very close, this equation changes to, we already studied this equation VA minus VB is equal to minus integral B to A E dot dl or E dl, since theta is equal to 0. VA minus VB, that is a potential difference that can be written as dV, is equal to minus integral B to A E dot dl or E dl, and E can be taken out. Since A and B are very close, there is not much change in the electric field. Electric field varies for a large distance only. When A and B are very close, electric field can be taken as constant. Therefore, it can be taken out minus E into integral B to A dl. What is integral B to A dl is the total distance between B and A, that is nothing but dx. So integral B to A dl can be written as dx. Therefore dV is equal to minus of E into dx, or E is equal to minus of dV by dx. Now this can be considered as another equation for electric field. Electric field is nothing but the negative gradient of potential. Electric field is nothing but the negative gradient of potential. So I am going to explain that fact. Before that, let us consider what is the unit of electric field. Since it is volt divided by distance, the unit of electric field is V by M. Okay. Now, what is the meaning of electric field is negative gradient of potential? That means electric field is always in the direction of decrease in potential. dV is the change in potential, minus dV means a decrease in potential. E is equal to minus dV by dx. I can write E proportional to minus dV. What's the meaning of that? Electric field is in the direction of decreasing potential. Minus dV is decreasing potential. So electric field is in the direction of decreasing potential. What is the significance of electric field? Electric field determines the motion of a positive charge in an electric field. So a positive charge will always move in the direction of electric field, because there exists a force F is equal to QE that causes the positive charge to move in the direction of electric field only. It will never move opposite to the direction of electric field. So the force or the charges, a positive charge always moves in the direction of electric field, and electric field is in the direction of decreasing potential. Let us club these two together. A positive charge always moves in the direction of decreasing potential, or a positive charge always moves from higher potential to lower potential. Once again, a positive charge, if it is movable in an electric field, it always moves from higher potential region to lower potential region. A negative charge will always move opposite. It will move from lower potential region to higher potential regions. So the electric potential is a physical quantity that determines the motion of a charge in an electric field.